All right. Here we are. We're moving quite a bit along in chapter 3. So we're covering this section 3.3 in two parts. So we're going to do the first half of it right now, and then just studying this increasing and decreasing behavior, and then we're going to do another half later. So the middle part of chapter 3, like it says here, is all about analyzing functions based on what we know about calculus. Okay, so at each point on this graph, we're going to start by trying to figure out where this graph is increasing, and we're going to think of it from the perspective of the slope at each point. So I want you to move along this graph. At each point, I want you to put a blue plus sign if the slope is positive at that point. I want you to put a red minus sign if the slope is negative at that point, and then a green 0 if the slope is 0 at that particular point. Okay, so if we compare our graphs, right, all of these portions here should have little plus signs, and then the slope in all these locations is also positive, so we have little plus signs there. It's no coincidence that this is also where the graph is increasing, right, on those intervals. In between, right, we have 3 little minus signs, a minus, a minus, a minus. And of course, our graph, right, along that stretch is decreasing, right? Meaning it's heading lower and lower and lower on the y-axis. In between, of course, we've got our green zeros right here and here. And because the slope is 0, we know those are critical numbers, right? And then usually what those critical numbers are is that they are little separators of where a graph might change from increasing to decreasing or vice versa. So in between, right, we have, right, these little green spots where the slope is 0 just for a moment. But again, they stand to be separators of the different behaviors of this function. So what we have by definition then is that f is increasing for all x in AB, where f prime is positive. So this is one way that we note positivity, right, by using the greater than 0 notion. So as long as the derivative is positive, actually let's clean that up a little bit, right, we know that f is increasing. And oppositely, we have the fact that f is decreasing for all x in the interval AB, where the derivative f prime is negative, right? And again, we're using that inequality to denote negative, meaning less than 0. All right, so these facts, right, that we can establish that the derivative being positive or negative tells us something about the function is what we are going to focus on today. So let's kind of read this, take a moment and read the next little section here to yourself. I particularly love the part in the middle where it says, in business, we might want to ask when our projections and data models tell us that our expenses, revenues, profits are increasing or decreasing, right? In engineering, we may want to find out when the useful life of a pacemaker, microchip, or bridge starts decreasing. Okay, and it's really interesting if you have not looked up or read about this concept of planned obsolescence. It's a great term to Google and read more about because it's very interesting what Apple has done to the universe. And then lastly, right, epidemiologists are people that study disease and super, common right now during the pandemic, right, is that they might be curious when the prevalence of a certain virus starts to decrease. So in sum, right, it says that function analysis is a powerful skill. Now, do these people, right, in the business and in the engineering and in the sciences, do they use their hands to take derivatives and establish places where a function's increasing or decreasing? No, we know that they don't. But the person that wrote the computer program that they use to decide where a function might be increasing or decreasing probably does, right? And that knowledge, that foundational knowledge about the behavior, right, of these derivatives and what it means about a function is really important from that perspective, right? So you know, someday you might go on to do bigger and better things using technology to do the analysis instead. But the underpinnings, right, is what makes you understand that technology even better. So let's tackle doing an analysis here. Okay, here's a cubic function, right? X cubed minus 3/2 x squared. Functions like this might be difficult to graph. Okay, we can't really graph it on the quick. So what we can do is we can use calculus to kind of at least try to figure out where it's increasing or decreasing. So the direction state for each of the following examples, state the intervals where the function's increasing or decreasing, and then justify your answer. And that is a bolded phrase that we use from the AP exams, and that your justification is really important, you know, to scoring as high as you can. So the first step it says here is that we're going to find critical numbers. So let's take the derivative, 3x squared minus, let's do the power rule here, we just get 3x, and then we have to set that equal to 0. Factoring out the GCF, I get this. I get one equation here, one equation here. Dividing by 3 and adding 1 to both sides here, I get 0 and 1. Okay, so my critical numbers, the two x values where this function might change from increasing to decreasing, doesn't mean it has to, are 0 and 1. So now what we're going to do, the second endeavor here, this is going to be new for us today, and it's this idea of creating a sign chart, right? And all a sign chart is it's an organization, like it's a nice way to stay organized to analyze the signs of a derivative. Okay, so it's an organizational mechanism. That's what it is. So we are going to take and just basically make a number line, and we're going to put our critical numbers on there, on that number line. Okay, now it's very proper to also label it. We are making a first derivative sign chart, right? So we are going to put f prime nearby. And then what we're going to do after our critical numbers are on there is that we are going to pick test points. So in this first interval right here, I'm going to pick a test point, and I'm going to use the number -10, okay, because that's left of 0, right? And what I'm going to do is I'm going to find the most factored version of f prime, which is right here, and I'm going to plug -10 into that. Okay, and I'm going to figure out the sign of my answer. I'm not really interested in the magnitude, right? So when I plug it in there, I'm thinking 3 times -10, and I'm just kind of thinking in my head that that's negative, right? That's the 3x part, and then the x minus 1 part, -10, minus 1, right? That is technically negative again. So what I basically have is a negative number times a negative number, and then that equals a positive result. So I'm going to put a plus sign here, because on that entire interval, if I were to pick -1, -2, -1,000,000, right, every derivative would end up being positive. Okay, now in the middle, right, I have to find a test point between 0 and 1. Most logical number on the planet is 1/2. Okay, same idea. I'm going to plug 1/2 into the highlighted pink derivative, because it's very easy to determine signs from that factored form. So in my head, let's kind of get rid of this. I am thinking 3 times 1/2. I don't care what number that is. I know that's 3/2, but really I'm just interested that it's positive. And then the other term is x minus 1, so I'm thinking 1/2 minus 1. in my head is negative. So my overall result will be negative in this portion of the interval. And that's true for every number in between 0 and 1. Out here, my favorite test point is a positive 10. Okay, and then I'll do the same thing. I've got 3 times 10 in the pink highlighted derivative, right, which is positive, and then 10 minus 1 is also positive. And when I multiply a positive times a positive, I get positive. So this tells us that this function increases, decreases, and increases. It's very much like similar to like the picture that we dealt with in the beginning. Okay, so in order to answer and justify this, my answer is going to say f is increasing. Okay, we're going to use our interval notation. So I'm going to say it's increasing on this interval and it's increasing on this interval. So I'm going to say from negative infinity to 0 in union symbol, 1 to infinity. And that is because, here's the justification part, f prime is positive. Okay, then I'm also going to say, let's go orange here, f is decreasing, and it's okay to use DEC on the interval, right? That one in the middle there, from 0 to 1. And then I have to say, the reason I know that is because f prime is negative. So that means, hearkening back to the beginning, that in that entire interval, I'd have a bunch of red minuses at every point. Okay. Now, polynomials are usually pretty easy, like this case here, to do. Things work out nicely. We can mess around with some other types of functions that may or may not be nice as well. So really you'll see example 2, example 3, example 4 is just switching up what kind of function we are working with. And then it's still going to be the same 3 steps. Find your critical numbers, create a sign chart, present an answer with justification. So let's do critical numbers here, right? F prime is going to be a composite derivative, right? Because 2x squared plus 1 is plugged into ln of x. So the derivative of the outside function is 1 over 2x squared plus 1. And then the derivative of the inside function is just the derivative of 2x squared plus 1, which is 4x. So when that looks nice and neat, we would have this. Now, I have a quotient here for my derivative, so I'm going to do 4x equal to 0, and I'm going to also set 2x squared plus 1 equal to 0, and see what critical numbers I get. One critical number is 0, and when I try to solve this, I get x squared equals negative 1/2, and we know by the nature of multiplication that that has no solution, because any number squared is going to be positive. Okay, so I'm working with one critical number here. So step 2 then is to organize my signs in a sign chart. So I'm going to put 0 down here. I'm going to label it f prime. And then I'm going to switch colors because I want to start thinking about little test points. So I love to use negative 10 and positive 10. And then plugging those in to this derivative. Okay. So here's what's interesting, is as we just noted over here, this has no solution because any number squared is positive, right? So think about that. And then think about the denominator that we're looking at here. 2x squared plus 1 is also always positive. So I have basically 4x divided by a number that is, or an expression, I guess, no matter what you plug in, it's always positive. So it doesn't really affect, that division doesn't really affect, right, the sign of my result that I would put in my sign chart. Okay, so I'm going to plug in negative 10 just to the numerator and do 4 times negative 10. I have a positive number times a negative number, right, and that's going to be negative. When I switch to my other test point of positive 10, I'm going to do 4 times 10 to get 40, right? But it's not interesting that it's 40. It's interesting that it's positive. Okay, and then this is my result here for this function. Now we're going to go ahead and present our answer, right, by justifying. So we would say that F, let's keep it same color, shall we? How much of your life do I waste making sure my colors are adorable? So we would say F is increasing on the interval 0 to infinity because F prime of X is positive. Okay, so remember that we're talking about this portion right here. Make sure you don't confuse your critical numbers with your test points. Okay, and then we would switch gears and we would say F is decreasing on negative infinity to 0 because F prime of X is negative. And that would sum that up. So example 3 gives us a quotient. So let's go ahead and work with the quotient rules since we haven't in a while. Let's take the derivative. So G prime should be low, D high minus high. D low is just 1. I'll put it there, and then all over the denominator squared. So if we're thinking along the lines of solving this, we want to factor the numerator, and then the denominator is fine as it is. We don't ever want to square that out. It's going to make it harder to make a sign chart. So the only thing in the, what we could do in the numerator for a minute, I guess, is distribute the 2x to come up with 2x squared plus 2x minus x squared, and then that would simplify to x squared plus 2x all over x plus 1 squared. And I want to take that one step further and fully factor it because that makes making sign charts easier. Holy Moses, we have a lot of factors here. That means it's going to take a lot to make a sign chart. So let's finish getting critical numbers. I'm going to set the top equal to 0. And then I'm going to set the bottom equal to 0. That's not the bottom. Oh my Lord, isn't that hideous? But let's go with it. X plus 1 squared. So if we square root that, like we know that since it's that quantity squared, right, we can really just reduce it that x plus 1 has to equal 0. And then I get negative 1 as one critical number. And then up here, I get 0 as one critical number. And then this gives me x equals negative 2 as a third critical number. Oh, the insanity. So let's put them in order. Negative 2, negative 1, and 0. And then let's label this f prime. And then let's go ahead and start to work on the signs here. So that means I'm going back to this most factored version of the derivative, and I am plugging my test points in there. So I'm going to use test points, negative 10, negative 1.5, negative 1/2, and positive 10. Now this looks like a pain in the butt. However, the same thing that happened in example 2 is happening here. The denominator is always positive because no matter what number you pick, when you add 1 to it and then square that result, it's going to be a positive answer. And dividing by a positive number doesn't change the sign of anything. Okay, so the numerator is really all we have to plug the blue test points into. So I'm going to plug negative 10 in, right? So negative 10 times negative 10 plus 2, that is a negative times a negative. So that's a positive. Put that in the first interval. Then I'm using negative 1.5, right, times negative 1.5 plus 2. And I have a negative times a positive. So that overall result is negative. Then I have got a, let's see, change colors, negative 1/2. So now I'm going to do negative 1/2 and then negative 1/2 plus 2. That's going to be a negative times a positive. So also a negative, back-to-back negatives. That makes it interesting. And then let's go back to blue here. When I plug in positive 10, right? I have a positive times a positive, which, oh my god, which gives me more positive. Okay, so what we have now is we have this function that's going increasing, decreasing, and then decreasing again, and then increasing. So we have a moment where we have to ask ourselves a question. What is going on at -1? And the reason we have to ask ourselves that is because we have the back-to-back minus signs. So the question is does this function decrease and then decrease some more, right? It has a critical number in there, maybe where the slope is 0. Or does it decrease, like an asymptote maybe, right? And then does it decrease some more after that? What would that look like? So it's decreasing to -1. Oh, and then it keeps decreasing, right? Something like this, sort of a setup. Okay, so we're trying to analyze which is this. So let's get that out of the way and let's think about it. The way that we're going to know this is that we're going to plug in -1 to the original. So when I plug in g of -1, I get the numerator squared over -1 plus 1, and that is 1 divided by 0, right? That is obviously a vertical asymptote because my denominator is 0, okay? So since -1 is not in the domain of the original, we cannot list it, right? We're going to have to split up our interval in part 3. So when we justify this, that analysis is going to matter in step 3 here. So we can say f, nope, it ain't f. Ooh, and way back here, I should go back and label this g prime because this was a different function. So we would say g is, let's do the increasing intervals first. So we would say it's increasing from -infinity to -2 and from 0 to infinity, right? That is this interval here and then this interval here where all the derivatives were positive. Now, on that second part, we will say g is decreasing, okay? And so this is what we have. We can either say -2 to 0, right? Or we would say -2 to -1 and then -1 to 0. That's what this analysis right here forced us to consider. So since there's an asymptote there, we're going to say this, and we're going to split this interval up. Because it doesn't decrease through -1 because it doesn't exist at -1. So we're just going to say g is decreasing on -2 to -1 and -1 to 0. And then we finish off by saying, oh, because g prime is negative. And I notice up here I never wrote because g prime is positive because it's late and I'm tired. Okay, so those are our two justifications. So again, this interval is split because of the discontinuity at -1. Okay, now we're going to look at the antithesis to that in example 4. And then I think we'll do example 5 together in class, but you can try that one on your own when you get there. So in example 4, we're going to do the same things, find our critical numbers, take the derivative. Derivative of 1 is nothing. And then this part we have to think as 2x to the 1/3 if I'm going to differentiate it. So the derivative would be the 1/3 times 2, and then decrease it by 1. And I end up with 2/3 x to the -2/3, which isn't going to help me unless I rewrite it as what that means. So that is the cube root of x squared. Okay. We can't set the top equal to 0, so the only critical number is going to come from setting the bottom equal to 0, which looks like this. And because we're going to divide by 3, right, you can always reduce it down to that simplest portion underneath that radical, that really x is going to equal 0. That's going to be my critical number. So let's try to go a little bit quicker. Let's throw that on a sign chart. Let's label this G prime, and then let's go ahead and pick some test points. So let's try -10 and +10. You're free to choose -1 and +1, or -5 and positive, whatever you want to choose for your test points, go for it. But let's kind of analyze this in this derivative, right? So we're testing. We want to know what sign the derivative has. So the 2/3 is a positive number, right, when I look at that coefficient. So that's not really relevant. And if we think about the denominator, the fact that I square it immediately, right, when I put in a test point, -10 squared immediately makes it positive. Cube rooting it doesn't change the sign. So that means that no matter what, whether I plug in +10 or -10, I'm going to get 2 plus signs because I am squaring the test point immediately. Okay, and now, again, we are forced with a decision. Do I put -infinity to 0 and 0 to infinity? Or do I just say that this function is increasing everywhere from -infinity to infinity, right? Well, we don't know that answer until we analyze what's happening at 0, like we did in example 3. So we had to plug in 0, right? The original, that will tell us what the original function has, and then that'll tell us if we split it up or if we write that it's increasing over all real numbers. Okay, so I'm going to leave this one up to you, and then don't forget at the end for step 3, when you decide G is increasing on, you put the interval. Don't forget to write, because oh, God, I'm addicted to that. G prime of x is positive. Okay,